Okay, this video is covering the linear equalization assignment that I wanted to apply for our 4-PAM system. Now it turns out, I was thinking of doing mystery signal 3 and adding some channel effects, but it gets complicated. You have to tweak your code quite a bit because there starts to become interactions between the different methods that we use to counteract various types of distortions. For example, in this video I'm going to show you that the choice of clock synchronization algorithm will be affected by the channel, and it'll make some sense as to why that would work as we talk about it. So rather than doing mystery signal 3, I'm going to walk through some example MATLAB code that's applied to our 4-PAM system and show you different case runs and help you think through why you're seeing the kind of things that you see with this example. Okay, so let's get started. Linear equalization, it's going to be a video, and I'm going to ask you to answer some quiz questions about the video. All right, so first of all, I wanted to point out there's still some simplifying assumptions that we're using. These assumptions aren't realistic when you get down to everyday applications of a communication system, but we're just peeling away layer after layer of the onion. This is where we are, and in real life you'd have to go much deeper to get a practical system up and working. I think we all realize that. All right, so the simplifying assumptions that we're going to have for this example is that number one, there is going to be an effect of a non-ideal channel. We're going to model that, but it's going to be a simple model. All right, the linear model. In the real world, the models aren't necessarily linear. And then it's also fixed in time. It's not time varying. Okay, so it's a constant channel, which means that once we figure out some type of equalization, we can go back and we can apply that to the whole signal for the entire time. All right, and that brings us to another simplifying assumption that we've done throughout this class, and I've never really mentioned this much, but because I feel like it's somewhat obvious, but nothing's obvious till it becomes obvious. So the idea here that we will first apply everything into a sequence of operations is not completely the way it would work. All right, you've got this signal that's ongoing. You're doing this communications, like if it's you're playing back a video, you can't just wait till you have the whole video signal and then apply one set of corrections right after the other in a sequential fashion. Really, in a real system, you're going to do this. There might be an order to it, but you're applying all the effects relatively close together. So this idea of mixing them into separate, different blocks of code is artificial, and you should know that. Okay, but it helps us get insight into the system, and so we're going to still apply these things in sequence. All right, so finally, let's get to the work. What I'm going to show you is some MATLAB code in operation, and we're going to look at two different cases. The first case, we're going to assume we have an ideal channel. It's ideal in the sense that there's not going to be any kind of frequency distortion. There will be some noise added into the example, but it's just a little bit of noise. Okay, and it's ideal in the sense that there's just a pure time delay. It's a 2-sample time delay. All right, I could have made it a bigger time delay, I could have made it less. This is just an example. All right, there's no other delay from other positions in this impulse response. Okay, this impulse response is also at the symbol rate level. All right, so we have a delay of 2 symbols. Here's the symbol showing up in the second position. Okay, this is not done on a sample by sample basis, although I'm going to show you when I modeled this to make the signal, when I go into the channel, I do upsample that to where it has a sample by sample effect. All right, that's how you would actually implement any kind of channel modeling, is at the sample by sample domain. All right, so that's the ideal case. With the non-ideal case, what I'm doing is I'm throwing in a little bit of multipath. Okay, so we still have the main signal showing up here at 1, and then we have some delayed, delayed by 1 symbol and attenuated by 0.45, delayed by 2 symbols and attenuated by 0.05. All right, so this is an example of a non-ideal channel. It's not super hard to undo the effect of this one. And, it's a fairly simple model. All right, so if you had a more complicated channel, the model could get bigger or more complex. And the corresponding work that it would take to get the algorithms to work would be, correspondingly harder. All right, so the first thing I wanted to talk about when I go and run through the code is to look at case 1 and case 2 applied to 2 different clock recovery algorithms, because I've talked about linear equalization and clock recovery sort of, they go hand in hand because one affects the other. So we're looking at 2 different algorithms. The first is this decision-directed clock recovery algorithm where we counted on knowing what the symbol values were to come up with our clock recovery. All right, so when I open the MATLAB code, I'll show you the difference in the optimization routines that you use for decision-directed versus what we're going to use also is maximum power clock recovery. All right, so the maximum power doesn't depend on knowledge that you're generating symbols, okay, and that turns out to be useful to us whenever the channel gets kind of blurred, right? I say blurred because if you had multipath, the effect of a symbol is now being spread out over 3 symbols, okay? And so you don't know exactly what that symbol should be because it's being interfered with because it's blurred based on, sort of a cumulative effect of 3 symbols, okay? So in that sense, the maximum power clock recovery algorithm works a little better because it's just trying to find something that will, spread these decoded soft decisions as far as they can, and then we can count on the filter to try to undo the effect of the channel. All right, so I'm going to give you a preview of the answer. This one wins whenever you have some channel effects. Okay, so the questions we're going to answer, all right, the first question is, what happens under ideal channel conditions? Which of these 2 algorithms produces the tightest eye diagram? So we don't have to worry about equalization yet. We're just seeing, these 2 algorithms, do they both work? The answer is yes. And then it turns out that the answer is the decision-directed clock recovery algorithm works a little bit better, although I have to admit, it's not super obvious from the plots. Okay, but in general, that's the case. If the decisions aren't blurred, you can use that information to get a tighter soft decision diagram. Okay, the next question is, well, what happens when we use a non-ideal channel? And I've already talked about the fact that if you don't know exactly what the symbol values are going to be, if those are kind of spread because of the channel, that makes this clock recovery algorithm that's based on the decisions, it actually fails much faster than the max power clock recovery algorithm. Okay, so it turns out max power is the one that will work better, and you'll see it works much better. It works, whereas decision directed does not. Okay, and then one other thing I wanted to talk about in this video is the effect of the roll-off parameter beta. All right, we know that has to do with when to downsample at the optimal times, and it makes sense that linear equalization and downsampling times are closely related because you have to first downsample correctly before the equalization can have some hope of working. So those are interrelated. All right, so what we're going to see is I can get this to work pretty well for a large enough value of beta, but if I lower beta, okay, larger beta increases bandwidth but improves intersymbol interference. So if I lower beta, it generates more intersymbol interference to the point where I can't even take care of it with channel equalization. All right, so those are the questions I want you to look for, questions and answers that I want you to look for as you watch the MATLAB portion of this video. Okay, here's some code that I've put together to explore the application of linear equalization in our 4-PAM system. Okay, so what I've attempted to do is try to make the code a little easier to read. So I've set up some data structures to pass into subroutines. Okay, so for example, I have this function that generates the message, and if you go down far enough, you can collapse these functions to where it looks a little cleaner. All right, and so I keep doing that. I see I have this function to generate the message, and I can look at that, and I have some input sequence and make it into blocks and put a frame marker in there, and that's going to become important because I have to detect the frame mark before I can do equalization. Okay, so I've got this frame mark sequence in, and from the frame mark sequence I can get Y frame, which is the PAM sequence that corresponds to the frame mark. All right, so that covers that. Now going back to our code, we generate a message, then we modulate the message, and inside this modulator subroutine, there's a lot going on with implementing the effect of the channel. So let me go down and just talk about a few things about that. So into this modulator section, okay, I unpack the data structures that give me the parameters for this, and then it's the thing we've talked about before. You find that ratio of m over n, you upsample by m, okay, modulate or convolve that with the square root raised cosine pulse with the upsampled PAM sequence, and you get the sequence that's ready to be modulated. Then you modulate by the intermediate frequency right here. I added some random noise to that, all right? And then from here, this step, you get the channel parameters, okay? So you take C and you upsample by the upsample factor, all right? And that would spread this channel effect to the right sampling rate, okay? And then you can filter that. You filter the modulated signal with this upsampled channel effect transfer or impulse response, and you get the effect of the channel on the modulated sequence, all right? And then you downsample, scale it correctly. We've talked about all that before, and you get the actual signal that has now, in addition to carrier offset, symbol rate offset, random noise, we also have the ability to model a non-ideal channel. Okay, so we're going deeper into the onion as we add these impairments. Okay, so we have the modulator set up. Now we have our Costas loop. We're going to undo the Costas loop and get our our oscillator for demodulation. We're going to demodulate. We're going to do the receive filter step, all right? And so from there, we're ready to do clock recovery, all right? So here's the clock recovery parameters that you need. And if you go down, you can look at the algorithm for clock recovery. And I wanted to show you the place where there's two different algorithms in this subfunction. Okay, so the clock recovery algorithm, let me collapse that one back. Clock recovery is here, okay? So with clock recovery, we used, when we derived this for the first time, we used a decision-directed algorithm where we looked at the difference between the quantized value and the soft decision. We would square that difference and come up with a cost function. Okay, so when we did that, we ended up with quantized values showing up in the algorithm updates. Okay, so in this first loop, the dual Costas, we have QX1, that's where we're quantizing. Okay, same thing down here with QX2. We've quantized the soft decision because we're taking advantage of the fact that we know what the symbol value should be. And that gives us a little faster convergence. Things work better under idealized conditions. Okay, so if you didn't want to use the quantized values, and that's my point, the reason we don't want to use the quantized values, if we know that the channel might distort those, it might be a problem to assume that we know the exact channel values, okay, or symbol values. So you could go to just a maximum power kind of criterion. That's discussed in the book, but the main thing I need you to know is that there's just a difference in the updates, all right? We don't use the quantized values, we just use the soft decisions themselves, and we're trying to maximize the downsample, maximize the power of the downsampled signal, with the idea is that would have the information in it, it's roughly sampled at the right rate, and we could use equalization to make corrections from there. Okay, so two different algorithms, and you just choose which one you want to run by setting a little flag in the data structure that calls it. Okay, so I have algorithm type set right here. 1 is for maximum power and 2 is for decision directed. All right. Okay, so from here, I think we're ready to do some runs. The first case I have is ideal, the ideal case. All right, so we have just a pure delay in our channel, so there's no effect from the channel. Okay, and what I wanted to do is run this under the two different algorithms that we would have. The first one is decision directed, 2 for decision directed. So when I run this, I get, this is a color plot of the soft decision diagrams where I've lined this up with the true message values. All right, and so here is the soft decision diagram for decision directed. You kind of, this is with filtering, without filtering. There's no difference here because there's no need to filter. So these look pretty much exactly the same. Okay, and the idea is there's less spread here. This is a tighter eye diagram than if I move to maximum power. Okay, so to move to maximum power, I change the algorithm from type 2 for decision directed to type 1 for maximum power. And then these two algorithms, they use different mu values. The mu's for maximum power algorithm need to be much smaller. Okay, so I'm going to adjust those and then rerun this. And what you should see, and it does seem that way, it's not dramatically different, but this is a little wider. This in here is a little wider. We don't get quite as tight of an eye diagram here under maximum power. All right, this effect is even worse if you have a smaller beta. All right, so remember beta is that shape parameter. All right, so that was the answer to that first question that that talked about when you use an ideal channel, or if the channel has already been equalized, you might switch over to decision directed for clock recovery because you get a tighter eye diagram. Okay, so the next thing I wanted to do is move away from an ideal channel, all right, and make it one that's got delays in it. All right, so you see here we have this as the impulse response of the channel. This is at the symbol level. So after a delay of 2, you get the direct path coming through with a 1 there. And then if you had an indirect path that had a little more delay, you'd get a smaller amplitude in that next sample position. And this even has, a delay spread of 3 symbols. Okay.
we wouldn't, in practice, we wouldn't know this, all right? Remember, this is just a simulation. In practice, you would make some measurements on a channel, but it depends on exactly how you're operating that system. And that's why we need things to be adaptive, all right? But what we're doing here for a simplifying assumption is we're assuming this is a simple channel model of a non-ideal channel, all right? Just if you're curious, I also needed to normalize C because we don't have any kind of automatic gain control set up in this simulation, and we need the gains not to change too much, or we'll be too far off on our downsample values. All right, so that was just to sort of normalize things so I don't get a big shift in the gain. All right. All right, so when I run this, I'm going to shift it back. Well, let me go ahead and run it with the decision directed. Okay, so when I run this with, oh, I'm sorry, that's not decision directed. That's the correct, this is working, all right? So let me explain how I know it's working. All right, so what I did was I selected the clock recovery algorithm V1 for the maximum power algorithm for clock recovery, all right? Then what I did was I went through this correlation step to find the frames, all right? You already did that in your mystery signal 1 and mystery signal 2. So if I know where the frames are, that means I know where the symbol sequence, the known symbol sequence should be. So I know the known symbol sequence for the framework, and that should show up in this position for R. So the received signal, when I transmit S, I should get R. Did you catch that? That's important. I know what S is because that's the frame marker. And I know where it should be because I correlated it and I found it. All right, so if I know S and I know R, I can now apply this this equalizer algorithm to find the filter that will undo the effect of the channel. Okay, so I put in some debugging steps here, but basically the rest of this is just the algorithm that I already talked about and I've done some videos on for doing a matrix version of channel equalization. All right, so we go through all those steps that we did before, and we end up choosing an optimal filter F. All right, once we have that optimal filter F, we can apply that to our received soft decisions. Okay, so the soft decisions came out of the clock synchronization algorithm. So we have XS that we came up with, all right, and then we just filter that with F to clean things up, all right? So how good of a job did it do? Well, that's where you can go to this figure here. When I get the channel, when I put the channel modeling effects in and I run the optimal downsampling algorithm, these are the downsamples that I get, all right? And that's not a surprise to me because I know that there's delayed versions of symbols showing up with different amplitudes. So I'm spreading the soft decisions all over the place, okay? So I took those values. These are the XS values, right? I plugged them into that equalization for the cases where I know the exact symbol values, which is the frames, right? The frame sequence that I sent. Calculate the equalizer, run the signal back through the equalizer, and out comes this for soft decisions. All right, so you see it definitely cleaned up all of these errors. You have almost 30% errors showing up here because of the multipath. And when I ran it through the equalizer, it cleans all those up. It gives you a nice clean eye diagram. Okay, so that's the point of linear equalization. It's an important step to make any communication system practical because we know that channels do have, they're not ideal. All right, so the next thing I wanted to show you is what happens if I don't use that maximum power algorithm if I try to use decision directed. Okay, so if I switch this back to 2 and I make the gain, the muse correspondingly bigger, when I rerun this, now the soft decision algorithm can't really even get XS, the soft decisions, to be close enough so that the equalizer can fix it. All right. So it's trying. It just doesn't work because it's expecting these exact symbol values. Those symbol values are spread all over the place. The algorithm fails. Okay. So if I switch this back to 1, adjust the muse, run a different clock recovery algorithm, I get it back to where it's working. Okay, so hopefully that gives you an idea of how you would use a linear equalizer. In real life, this method is too simple. All right, you're not going to use a matrix inversion. You're not going to just detect the frames. You're going to adjust as you go. And there are some really sophisticated and mathematically elegant algorithms out there for doing channel equalization. This just gives you a glimpse of why it's important and how it might possibly work under some pretty simple conditions. Okay, the last thing I wanted to do in this video is talk about the roll-off parameter beta. So I made beta equal to 0.6, which gives it more roll-off, which makes symbol detection easier because there's less inter-symbol interference between each symbol. So if I make this 0.3 and rerun this algorithm, what's going to happen here is that it breaks it. All right, there's a brief period of time when the eye opens fairly consistently, but in general, things are it's just a little too hard to correct for this system. All right, if I had much less in terms of channel distortion, so what would that mean? Let's say we only had 0.1 of this amplitude on the multipath is reduced from 0.45 to 0.1. I think it might work. Yeah, in that case, it's back to being capable of equalizing the channel because you can handle that much of multipath with the presence of a lower beta. The lower beta gives you less bandwidth but more susceptibility to inter-symbol interference. And so doesn't it make sense to you that if I bump this number up, it's going to have more multipath and it's harder for the system to consistently, it started out being able to do it, but it lost track somewhere and got out of sync and started to fail. Okay, so hopefully you get some insights on that. We're going to move on away from linear equalization and go to more, or different topics from digital communications.